Good afternoon, everyone. This is Weina. Maybe very few of you just saw me many times. This is actually my fourth presentation in this ACI convention. So thanks for my PhD advisor, Dr. Kamal Kaya, to bring me into this very interesting session. I learned really a lot. So I will present something a little different as introduced. I will just use the cellulose nanocrystals to coat the steel fibers and using the UHPC and to evaluate some of the properties. By the way, my name is Weina. My name is Weina Meng. I'm assistant professor from Stevens Institute of Technology. So today I will first of all introduce the research objectives and the significance. And then I will talk about the research approaches and then the discussions and of the results, and finally the conclusions. And by the way, this work is very preliminary, so I really welcome any comments and suggestions to improve our work. So the general background problem is the need to further improve the flexural properties of UHPC for extended applications. So there's actually many ways that can improve the flexural properties, such as control the rheology to have a better dispersion and reorientation of the fibers, or use multi-scale reinforcement, fiber reinforcement to increase the UHP. So there's many ways. So one of the very efficient or effective and promising method is to coat the steel fibers, so modify the steel fiber surfaces, because it can increase the fiber pullout force and energy, as you can see some of the literature results, and thus it can help with the improvement of flexural strength and toughness. So, however, for the current studies on the surface modifications, there are some challenges. So for one of the typical way is the plasma surface treatment. For this way, people use a plasma functionalize the steel surface with the hydroxyl groups, so that to improve the interface between the fibers and the cement matrix. However, this method is a little bit expensive. So also there's people use a zinc phosphorus coatings to coat on the steel surfaces, but this one shows very good improvements, like around 20% increase in the flexural strength. Sorry, I didn't put the toughness. So both the zinc and the phosphorus are pollutants for the water and also the soil. So the third one is also very common used the coating materials as nanosilicate. The nanosilicate coating on the surface shows very good performance in terms of improving the flexural properties. Is around like 25% increase in the flexural strength. However, as you can see here, the coating process is a little bit complicated. So therefore, our research objective is to use more cost-effective and environmentally friendly coating materials, which is the cellulose nanocrystals as a coating materials, and to develop like a easier coating process to modify the steel fiber surfaces. So by this way, we wanted to improve the bonding between the fibers and the matrix and to improve the flexural properties. And also, we will evaluate the effect of the CNCs, the coating effect on the key properties of the UHPC, and to understand the underlying mechanisms. And by the way, the cellulose nanocrystals is the natural materials, as natural materials, manufactured from like the cotton, the trees, and the tonicate. So there's many unique features of the CNCs. First, as I mentioned, it is environmentally friendly materials. It is cost-effective and low cost. And also very important is that it has abundant like hydroxyl functional groups. So on the surfaces, so it can form a very strong bond between the cement paste and these materials and promote the cement hydration. And also, the CNCs exhibit large surface area, high aspect ratio. Where is the high aspect ratio? Sorry, I'm not sure where I put it there. And the high elastic modulus and the tensile strength, and also the very low density. So due to this unique features, it has really just used for many applications, like to treat the some of the nanomaterials. But here, just in concrete areas, like people usually use it as addition to concrete to the cementitious systems. Just directly add the dry powders or the liquid suspensions into the concrete system. So as you can see, some of the literatures, the mechanical properties with the optimum dosages are significantly improved by using of these materials. And also the compressive strengths and the flexure strengths, as you can see, the optimum dosages shows a very significant improvement on the strengths. And also it can reduce the autogenous shrinkage by when people are using it into the system, in the concrete system. So just based on the literatures, there's many two effects for the enhancement. One is the CNCs, as I mentioned, is high Young's modulus, is high tensile strength. It have very good, and it's nano sized. And it provides a very good bridge effect, or bridging the nano scale and micro scale kind of cracks. By this way, it can improve some of the flexure properties and compressive strengths. And also, as the CNCs are highly hydrophilic and hygroscopic, so it could use that as an internal curing agents, or it has an internal curing effects that can promote some of the hydration and also supply some of the water during the hydration that can benefit to reduce the shrinkage. However, by just directly add the CNCs into the system, there's little problems. So basically, if you use lower amounts, the CNCs is hydrophilic, so it can disperse and well disperse in a water solution. But if you use a little higher, which is higher than 0.5% by mass of cement, then the severe agglomerations will be observed. And that will compromises the mechanical properties. So we think that if we coat the CNC materials on the steel fibers, is a better way to utilize such nanomaterials. And by that way, we can mitigate the agglomerations of the CNCs in a cement pore solution. So in this study, we proposed a way to coat the CNCs on the surface of steel fibers to improve the flexural properties. So here is our methods to coat the CNCs. First, we do a pretreatment for the pristine steel fibers. So the pristine steel fibers were immersed into the sodium hydroxide solution and for 30 minutes. And then we remove the residual the sodium hydroxide solution. And after that, for the step 2, is a coating process. We just immerse the pretreated steel fibers into the CNC suspensions with different concentrations for 1 hour. And then we dried it in the oven at 40 degrees C for 24 hours. Okay. And with that, we can have the CNCs coated on the surface of the steel fibers, generally through the hydrogen bond. So from the SEM observations, you can see that the pristine steel fibers is pretty smooth. But when you have the CNC coated on the steel fibers, you will see the surface is much more roughened. And the CNC particles are very well coated and uniform covered on the surface of the steel fibers. And from the EDS observations, we also observed that the CNC-coated steel fibers, there's like much more oxygen content on the surface, which prove that there's the CNCs are very well coated on the surface of the steel fibers. And also, by this coating process, we just decrease the contact angle from 71.9 degree to 54.5 degree. So which means we change the surface of the steel fibers to like very hydrophilic. And this hydrophilicity improvement is important because it will beneficial for densification of the ITZ between the fibers and the cement matrix. So now we know that the CNC can be well coated on the surface of the steel fibers. And the next questions for us is, how can we determine the concentration of the CNCs? So what is concentration we should use to coat the CNCs, or to coat the steel fibers? So here we conduct the rheology test. So we use an Antonpar rheometer and measured the mixtures with different concentration of CNCs, measured the shear stress and shear rates flow curves. And we use the Herschel-Barkley model to feed these curves and get a flow index N here. So the flow index can be used as an indicator of the CNC's agglomerations. As you can see here in this figure, so with a high flow index, we usually observe the good dispersion of the CNCs in the suspension. But when the flow index N starts to decrease, the CNC starts to agglomerate. So from this results, we have determined the preliminary threshold concentration of the CNC as 1%. So the further experiment have to be done to finalize this threshold concentration, as the CNC in water is very different than in cementitious systems. So here we investigated 4 different mixtures. One is the control. The control, we use a pristine steel fibers in without any treatment. And then we have 3 mixtures with different CNC concentration treated steel fibers. And here shows our mixture design. So we have a very high amount of 60% slag in a UHPC system. So here shows the workability. So the CNC's coated steel fibers reduces the flowability and also increases the air content of UHPC mixtures. But when the CNC concentration is no less than 1%, the reduction of the slump or the workability is not significant. But when we increase to 1.5%, you will see a significant reduction in the workability. So the reason is that when we use the CNC to treat the steel fibers after oven, and they stick together because a very high concentration of the CNCs, and the bond is so strong. And when we use as a kitchen mixers to mix it, we cannot actually very well disperse it or break those bonds. So I think that is a reason, and also because of that, this agglomerations of the steel fibers, we also have like a significant increase in the air content when the content of the concentration of CNCs is more than 1%, which is 1.5% in our case. So the good part of it is when we use the 1% CNCs to treat the surface of the steel fibers, we shows a good improvement in the compressive strength. And the better things is we shows a significant improvement in flexure strength and also the fracture toughness. But when it is increased to 1.5% for the CNC concentration, there's significant reduction. So we just figure out the enhancement mechanisms when we use 1% or less CNCs for treatment. So one of the reasons is the improvement in the physical interlock. So as we use the AFM testing, we found that the CNC's coated steel fibers has much higher average roughness than the pristine steel fibers. It's like around 4 times. And the increase of the average roughness of the steel fiber surfaces increase the physical interlock, and thus improving the bond between the fibers and matrix. And also, the good part of the CNCs is it can also improve the chemical reactions. So as they have abundant, like the hydroxy groups, functional groups, so it will react with the silicate and the calcium ions to form like more CSH in the ITZ, in the interfacial transition zone. So here is what we observed. So this is a pristine steel fibers, and this is CNC coated steel fibers. So the CNC coated steel fibers, if you look at the ITZ, it looks denser. So we do a quantification using the nanoindentation. And we observed the ITZ around the CNC coated steel fibers. It has more high density CSH and ultra high density CSH. And also it has much less pores in this area, in the ITZ in between. So because of that, because of improvement of the physical interlock and the promote of the chemical reaction, we have like significant improvement on the bonding between the fibers and the matrix. However, we have the improvement, but we also have the reduction. And as I mentioned, when we have the treatment, when we have the concentration around the 1.5%, we have the agglomeration, and we cannot really break the bond between the fibers. Maybe some of you maybe have a better solutions, but because of this, we could not have a good fiber dispersion in the system when the concentration, CSN concentration is greater than 1%. So we always need a good dispersion and orientation to get better flexural properties. But anyway, so here, this is why this reduction happened. I just want to emphasize that. So in conclusion, we can have the CNC, which is environmentally friendly and cost-effective kind of materials to coat the steel fibers to enhance the bond between the steel fibers and matrix to improve the flexural properties. And we can use the rheology test to preliminarily determine the threshold concentration of the CNC content. However, for now, for 1%, we can have it perform very well, but beyond that, we have a problem for the bonding or the agglomeration of steel fibers, and the research still needs to be done here. And I will welcome any suggestions and comments on this subject. And I would like to thank my very hardworking and very excellent PhD student, Mr. Zhang Du and Ms. Yuhuan Wang. And thanks for our sponsor, NSF and US Army. Thank you very much for your attention. And I would like to take any questions if you have. Thank you.